Now, shall we learn about shapes of atomic orbitals? Children, we know what Schrödinger wave equation is. It is H operator psi equal to E psi. When we solve Schrödinger wave equation, we get the values of psi. Psi is a wave function for an electron in an atom moving in the form of waves. Okay, when scientists plotted graphs between psi as a function of r, which is nothing but the distance of the electron from the nucleus, they got different graphs for different orbitals. The figures displayed show such graphs for 1s and 2s orbitals respectively. Now let's take a look at the first graph. We know for a 1s orbital the value of n is 1 and L is 0. When the values of psi corresponding to the electrons in 1s orbital were plotted against r in the graph, we get the first graph. Now let's take the second graph. We know that for a 2s orbital, the value of n is 2 and L is 0. When the values of psi corresponding to electron in 2s orbitals are plotted against r in the graph, we get the second graph. Although both are s orbitals, they have different n, different values of n or principal quantum number. That is, 1s orbital occupies first shell and 2s orbital occupies second shell. We also find that 1s orbital has a curve that is totally different from that of a 2s orbital. However, psi has no physical meaning. It is simply a mathematical function of the coordinates of an electron present in an atom. Later, it was the German physicist Max Born who showed that the square of the wave function psi, that is, psi square at a point, gives the probability density of finding an electron at that point within an atom. The graphs displayed show the variation of psi square as a function of r for 1s and 2s orbitals respectively. What is r here? R, it denotes the distance of the electron from the nucleus. Here again, the curves for 1s and 2s orbitals are different, isn't it? Now let's focus only on the graph for 1s orbital. When a graph was plotted between psi square as a function of r against r for an electron in 1s orbital, we observe that the probability of finding a 1s electron very close to the nucleus was very high. And as we move away from the nucleus, the probability sharply decreased and became almost zero. Right? Now, look at the graph obtained for an electron in 2s orbital. For the 2s orbital, on the other hand, the probability of finding a 2s electron right next to the nucleus was almost zero. Do you see? The curve is a little away. When you compare the curve obtained for a 2s electron with that of the curve obtained for 1s electron, you can see that it starts a little away from the y-axis. So, a little away from the nucleus, the probability of finding a 2s electron is very high, and then it decreases and touches zero, and then all of a sudden it increases. The probability of finding a 2s electron increases, and then it reaches a maximum, and again it decreases and approaches zero as the value of r increases further. Look at the curve where it first touches the x-axis. At this place, which is at a certain distance around the nucleus, the probability of finding a 2s electron is almost zero. The region where this probability density function, that is psi square r, reduces to zero is called nodal surface, or simply a node. So what is the definition of nodes? Nodes or nodal surfaces are areas where there is no probability of finding the electrons of a certain orbital. Now, how would you find out the number of nodes for an ns orbital? We can use the formula n-1, where n is the principal quantum number. Now, I have taken the examples of 1s, 2s and 3s orbitals, and let's try to find out the number of nodes possessed by each of them. Now coming to 1s orbital, the value of n for a 1s orbital is 1. So if we substitute 1 in place of n in the formula n minus 1, you get an answer of 0. This means that 1s orbital has no node. And this is also evident from the graph plotted between psi square and r for a 1s orbital. See, there is no node in the graph. Now coming to 2s orbital, the value of n for 2s is 2. So the answer you get when you substitute the value of n in n minus 1 is 1. So 2s orbital has one node only. And this is also evident from the graph plotted for 2s orbital. There is only one node, isn't it? Now coming to 3s orbital, the value of n is 3. So 3 minus 1 gives you 2. So therefore 3s orbital has two nodes. Now look at the picture shown in the right bottom corner. Okay. The number of nodes in an orbital increases with increase in the value of n, isn't it? When the value of n increases, you can find that the number of nodes also increases, as displayed in the picture. It is possible to visualize these probability density variations shown in the graphs plotted between psi square as a function of r against r in the case of 1s and 2s orbitals in the terms of charge cloud diagrams. When scientists solved the Schrödinger wave equation, they got different values of psi square. They plotted each solution of psi square as a dot. So, a dot in the charge cloud diagram represents the probability of finding an electron at that point at a given point of time. Or, a dot in the charge cloud diagram represents the location of an electron around the nucleus at a given point of time. Now, if you look at the charge cloud diagrams of 1s and 2s orbitals, the cloud of negative charge is denser at certain areas. This indicates the probability of finding the electron is maximum in such areas. Let's focus on the charge cloud diagram of 1s orbital. Now, the electron clouds do not have sharp boundaries. Fine? Because even at large distances from the nucleus, there lies a least chance of finding a 1s electron. Same is the case with 2s, 3s, 4s electrons found in respective orbitals, and so on. Hence, for the sake of convenience, we draw boundary surface diagrams. Now, I want you to imagine the electron charge clouds of 1s and 2s orbitals three-dimensionally. I told you in our previous class that an atom, since it is the basic constituent of matter, should be imagined three-dimensionally. Okay. So, in boundary surface diagrams, we enclose the region of space around the nucleus where there is 90% chances of finding a 1s electron in a sphere. Same is the explanation when it comes to 2s, 3s, 4s orbitals and so on. So, the charge cloud diagrams are nothing but probability density plots which give us an idea of the orbital with dots. But when we try to enclose it in a sphere three-dimensionally, we call it the boundary surface diagram. Okay, boundary surface diagram for an s orbital is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which the probability of finding the electron is about 90%. Shapes of s orbitals. For s orbitals, the value of the azimuthal quantum number L is 0. Hence, the magnetic quantum number ML can have only one value. Now, how did you come to know that ML can have only one value? Remember, you would have learned from our previous classes about a formula 2L plus 1. This formula can be used to calculate the number of values possible for ML of any orbital. Now, for an s orbital, the value of L is 0. If you substitute 0 in place of L in the formula 2L plus 1, you get 2 into 0 is 0 plus 1 is equal to 1. So ml can have only one value, and that one value is assigned as 0 for an s orbital. So this means that s orbital can have only one orientation in space. This means that the probability of finding the electron in s orbital is same in all directions at a particular distance from the nucleus. Okay, hence s orbitals are non-directional and spherically symmetrical in shape. Here I have displayed the boundary surface diagrams of 1s and 2s orbitals. You can see that the 2s orbital and 1s orbital are spherical in shape, but the only difference between them here is the 2s orbital is bigger in size than the 1s orbital. S orbitals increase in size with increase in the value of the principal quantum number. Hence, a 4s orbital is bigger in size than a 3s orbital, and this is bigger in size than a 2s orbital, which in turn is bigger in size than a 1s orbital. Also, s orbitals increase in energy with increase in the value of the principal quantum number n. So, the energy of electrons occupying 4s orbital is greater than the energy of electrons occupying 3s orbital. This is greater in energy than 2s orbital, which in turn is greater in energy than the electrons occupying 1s orbital. This is because as the size of the s orbital increases, the distance of the electrons occupying the higher s orbitals increases from the nucleus. As a result, their energy increases. Okay, hence s orbitals increase in energy with increase in the value of the principal quantum number n. The charge cloud diagrams of 1s and 2s orbitals are displayed. Here, if we take 1s orbital, the electron cloud density or the probability of finding electrons in 1s orbital is maximum around the nucleus, and it decreases with increase in the distance of the electrons from the nucleus. Now for a 2s orbital, the 2s orbital consists of two spherical regions of high electron probability. In between the two spheres, there is a region where the probability of finding an electron is 0, and this is called a node or nodal surface. So, a node or nodal surface is nothing but a region where the probability of finding an electron is 0. S orbitals have radial nodes. Remember how we calculated the number of radial nodes for an ns orbital previously? We used the formula n-1 where n is the principal quantum number. I stress this because when we move on to study about the shapes of p orbitals, you will be coming across yet another formula for calculating the number of radial nodes for an np orbital, which is different. Okay, so keep this in mind and prepare for your exams. So when we take the case of 1s orbital, we find that it has no node. Okay, because for 1s orbital the value of n is 1. So if we substitute in this formula n-1, it becomes 0. This means 1s orbital has no node, whereas 2s orbital has one radial node. Now what about the shapes of p orbitals? Instead of s orbitals, which are very spherical and symmetric in shape, the p orbitals are not symmetric. For p orbitals, the value of the azimuthal quantum number L is equal to 1. If L is 1, then the minimum value of principal quantum number for p orbitals has to be n is equal to 2. This means that you can find the existence of electrons in the p orbitals only from the second shell onwards. But you cannot find the existence of electrons in p orbitals in the first shell. Okay, you can find the electrons existing in p orbitals only from the second shell onwards. Okay, this is because the value of L cannot be greater than n-1. That is, it cannot be greater than 2 minus 1. Hence, the magnetic quantum number ML can have 3 values. Now, how did you come to know that ML can have 3 values? This you have learned from our previous classes. Okay, the value of ml can be calculated from the formula 2l plus 1, where you substitute the value of L. Since this is a p orbital, the value of L corresponding to it is 1. Okay, now 2 into 1 is 2 plus 1, it is 3. Okay, that's how you get 3 values for ml. And the 3 values can be minus 1, 0 and plus 1. This means that there are 3 p orbitals which can have 3 orientations in space along the x, y and z axis. They can be designated as px, py and pc. You can just have a look at the adjacent picture which shows the shapes of the 3 p orbitals, px, py and pz. In these diagrams, the nucleus is at the origin. Each p orbital has 2 sections called lobes that are on either side of the plane passing through the nucleus. Okay, if you take the case of pz orbital, the plane that is passing through the nucleus is that of an xy plane. Okay, the probability of finding the p electrons is maximum in the 2 lobes on opposite sides of the nucleus. This gives rise to a dumbbell shape for p orbitals. So p orbitals in general have a dumbbell shape. The probability of finding the p electrons is 0 in the nucleus, that is at the origin, or in the plane where the 2 lobes touch each other. This plane is also called as a nodal plane. Okay, there are 3 p orbitals in every shell. Now what makes them different? Just imagine all the 3 p orbitals together in an atom. Okay, the 2 lobes of each p orbital have negatively charged electrons in them. Now, since they are negatively charged, they repel each other. Now, what could be the shape in which they orient themselves in each shell so as to have minimum repulsion between them? Okay, since the electrons in the lobes of each p orbital repel each other, they would orient themselves in a way where they can be existing at maximum distance between them. And that orientation is possible when you imagine these 3 p orbitals to be perpendicular to each other. That is, if one of these orbitals is along the x-axis, then the second p orbital should be along the y-axis, and the third p orbital should be along the z-axis. In this way, the 3 p orbitals are oriented along 3 axes. Now, that explains why p orbitals, that is px, py and pz orbitals, have 3 orientations in space. In the absence of an external magnetic or electric field, all the 3 2p orbitals have the same energy. Such orbitals having equal energy are called degenerate orbitals. P orbitals increase in size and energy with increase in the value of the principal quantum number. You can see from the trend or order shown that the size of the 3 4p orbitals is bigger than the size of the 3 3p orbitals. The size of the 3 3p orbitals is bigger than the size of the 3 2p orbitals. And you can also see that the energy of 4p orbital is greater than that of 3p orbital, and the energy of 3p orbital is greater than the energy of 2p orbital. The 2 lobes of each orbital are separated by a plane having 0 electron density. Okay, this plane is called a nodal plane. For example, in the case of pz orbital, xy plane is a nodal plane. Okay, this means xy is the plane passing through the nucleus on which the probability of finding the electron is 0. Okay, you can see at the center or the origin, origin means it represents the nucleus. Okay, the probability of finding an electron there as it is seen in the 3D model is 0. So the plane, xy plane passing through the nucleus on which the probability of finding the electron is 0 is the nodal plane in the case of pc orbital. This is also called angular node. Okay, the number of angular nodes in any orbital is equal to the value of the azimuthal quantum number L. For p orbitals, according to the notation, the value of L is equal to 1. Therefore, the number of angular nodes in p orbital is 1. Now, look at the charge cloud diagram shown for 4p, 3p and 2p orbitals. Now let's just focus on the charge cloud diagram of 2p orbital for explanation's sake. You can see a red dot in the center, isn't it? This represents the nucleus where the probability of finding an electron is 0. Now you can see a tiny space in between the nucleus and the start of electron cloud density in these diagrams. This means that the probability of finding a 2s electron in a 2p orbital very next to the nucleus is 0, whereas a little away from the nucleus the probability of finding a 2s electron is very high. Okay, and you can see that the electron density decreases with increase in the distance of the electron from the nucleus. You can apply the same explanation for 3p and 4p orbitals. The p orbitals with a value of n greater than 2 have radial nodes. Radial nodes are nodes found in the orbitals along the radius of an atom. So, 2p orbitals do not have radial nodes. Only those p orbitals which are present in third shell, fourth shell and so on have radial nodes. Okay. Now, how to calculate the number of radial nodes for an np orbital? Using the general formula n minus 2. We can calculate the number of radial nodes for any np orbital, where n is the principal quantum number. So, the number of radial nodes in 2p orbital can be calculated as follows. Okay, we know as per the notation, the value of n is equal to 2 in 2p orbital. So, substituting 2 instead of n in the general formula n minus 2, you get a value of 0. So, this means that 2p orbital has no node. Now, let's take the example of 3p orbital. As per the notation, the value of n in a 3p orbital is equal to 3. So, when you substitute 3 in place of n in the general formula n minus 2, you get an answer 1. So, this means that 3p orbital has one node in it. Now, what about the shapes of d orbitals? For d orbitals, the value of azimuthal quantum number L is 2. If L is 2, then the minimum value of principal quantum number n for d orbitals has to be 3. So this makes it clear that you can find the existence of electrons in d orbitals only from the third shell onwards. You cannot find the existence of electrons in d orbitals in the first shell or second shell, but you can find the existence of electrons in d orbitals only from the third shell onwards. This is because the value of L cannot be greater than 2, that is n minus 1. 3 minus 1 gives you 2. Okay. Now, the magnetic quantum number ml can have 5 values. You would have learned how to calculate it from our previous class. You would use the formula 2l plus 1 where you substitute the value of L as 2 and you get 2 into 2 is 4 plus 1 which is 5. So this means the quantum number ml has 5 values for d orbitals. And these values can be minus 2, minus 1, 0, plus 1 and plus 2. This means that there are 5 d orbitals which can have 5 orientations in space along the x, y and z axis. And they can be designated as dxy, dyz, dxc, dx square minus y square and dz square. Now look at the adjacent picture. Here I have displayed the shapes of all the 5 d orbitals. Now, look at dxy, dyz and dxc. Their shapes are almost similar. If you take the case of dx square minus y square, there's the difference in that the 4 lobes are oriented along the x and y axis. Okay, now if you take the case of dz square, it's a totally different shape. Okay, here you can find the two lobes oriented along the z-axis. It's that of a donut shape. Now you can see that in the first four d orbitals, instead of dz square, if you take the case of dxy, dyz, dxc and dx square minus y square, you can see four lobes. Okay, these lobes represent the space around the nucleus of an atom where there is maximum probability of finding electrons in d orbitals. If you take the case of dxy orbital, here the four lobes, they are oriented in between the x and y axis. Okay, and this can be taken as a plane which is perpendicular to the z axis. If you take dyz orbital, you can see that the four lobes in dyz orbital are oriented in between the y and z axis. Okay, if you take these lobes to be in a plane, then this is perpendicular to the x-axis. Now if you take dxc orbital, you can find that the four lobes in dxc are oriented in between the x and z axis. Now when you take dx square minus y square, the four lobes are oriented along the x and y axis. So this is about the shapes of the 5d orbitals. Now the shapes of the d orbitals for which the value of principal quantum number n is greater than 3 are similar to 3d orbitals, but the only difference is that they differ in their size and energy. Now let's look at the energies of d orbitals. In the absence of an external magnetic or electric field, all the five 3d orbitals have the same energy. Such orbitals of the same subshell having equal energy in the absence of external magnetic or electric field are called degenerate orbitals. Okay, so in the absence of an external magnetic or electric field, all the five 3d orbitals are degenerate. Okay, they are degenerate orbitals since they all have the same energy. D orbitals increase in size with increase in the value of the principal quantum number. Okay, now look at the trend shown. The size of all the five 5d orbitals is bigger than the size of the five 4d orbitals, and the size of all the five 4d orbitals is bigger than the size of the five 3d orbitals. Now what about the energy of these d orbitals? What happens to the energy of the various d orbitals with increase in the value of the principal quantum number? It's the same as the trend observed in the case of size of various d orbitals. You can see that the energy of the electrons in 5d orbitals is greater than the energy of electrons in 4d orbital, and the energy of the electrons in 4d orbital is greater than the energy of electrons in 3d orbital. What's the reason? This is because as the size of the d orbitals increases, the distance of the electrons occupying these higher d orbitals increases from the nucleus, and as a result their energies increases. Okay, this is the reason for increasing trend observed in the energy of the various d orbitals with increase in the value of their principal quantum number. Now I've taken the example of a dxy orbital to explain you about angular nodes found in d orbitals. Look at the 3D model of dxy orbital. There are four lobes and these lobes are oriented in between the x and y axis. They represent the probability of finding the electrons in between x and y axis. You can also see that the probability of finding an electron in the origin, okay, or the node is 0. Since the origin represents the nucleus of an atom, the probability of finding an electron in the origin or the nucleus of an atom is 0. Now look at the 3D xy orbital shown in the adjacent picture. You can see that there are two nodal planes passing through the origin. You have two planes passing through the node or the origin and bisecting the xy plane containing z-axis. This means that there are two planes passing through the nucleus on which the probability of finding an electron is 0. Such nodes are called angular nodes. Okay. Since the number of nodes correspond to the number of bisecting planes, angular nodes can also be called planar nodes. So the number of planar or angular nodes in an orbital is equal to the value of its azimuthal quantum number L. Since L is equal to 2 for d orbitals, the number of angular nodes in d orbital is 2. Finally, we have two general formulae, one for finding out the number of radial nodes in any orbital, and the second one is for finding out the total number of nodes for any orbital. Let's look at the first formula. For finding the number of radial nodes in an orbital, you have the formula n minus L minus 1, where n stands for principal quantum number and L stands for azimuthal quantum number. I have taken two examples. One is that of a 2p orbital and the second one is that of a 4d orbital. Okay, so for 2p orbital, from the notation itself, it is clear to us that the value of n here is equal to 2. And since this is a p orbital, the value of L corresponding to a p orbital is equal to 1. So the number of radial nodes in 2p orbital is obtained by substituting the values of n and L in the formula n minus L minus 1. So you get 2 minus 1 minus 1, which is equal to 0. From this, it is clear to you that there are no radial nodes in 2p orbitals. This we have already looked at when we were discussing about the shapes of p orbitals. Now, for d orbital, the value of n is 4, and since this is a d orbital, the value of the L corresponding to it is 2. So the number of radial nodes in 4d orbital is given by 4 minus 2 minus 1, which is equal to 1. So there is one radial node in a 4d orbital. The next formula is for calculating the total number of nodes for any orbital. The formula is n minus 1. Here n stands for principal quantum number. This formula is obtained as the sum of L angular nodes and n minus L minus 1 radial nodes. So if you take the sum of these, you get the total number of nodes for any orbital as L plus n minus L minus 1. This obviously is equal to n minus 1. So if you want to calculate the total number of nodes for any orbital, you can use the formula n minus 1. So thank you children for patiently listening to me.